discuss about the two-port networks. Chapter number 5 in our network theory. So we discussed already magnetic coupled circuits in the last session, and in this session we are going to spend on some time on two-port network analysis. Okay, so how do you define certain terms here? Number one is, what is a port? How do you define a port? A port is what? A pair of terminals where the energy is either injected into the network or else received from the network. A power is injected into the network or power is taken from the network. That pair of terminals is called what? Port. Understand all of it? Okay? Port is nothing but a pair of terminals. It is a pair of terminals. A pair of terminals. Okay, where the energy is either supplied or received. Yes or no? Or received. So you call it port. One port network. What is a one port network? A network with one pair of terminals. So in that one pair of terminals, if it is a one port network, look at this, all of you. You will have only one pair of terminals. Say this is 1, 1 dash. Either the energy is supplied. Say this is Vs and this is Is. Source it is acting like. And now you are injecting the current into the network. You are injecting the energy into the network. Or else you can also, this is any one port network. Let us say this is one port network. Let us say, because it has got only one pair of terminals where the energy is now received in this case. Now it is a load. Now this is a load. So you have VL and this is IL. You are now taking the power from the source or energy from the power from the network or energy from the network. So this is called one port network. Then what is a two port network? It will have two pairs of terminals. It will have two pairs of terminals, okay, where the energy is supplied at one pair of terminals called input port, and energy is received from the pair of terminals called output port. So this is input port network, input port terminals, and these two are called what? Output port terminals, V2 and I2. This is called two-port network. Similarly, you may also have an N-port network. N-port network. N-port network is having N pair of terminals. N pair of terminals. Okay, look at this. This is first port, 1, 1 dash. This is second port, 2, 2 dash. This is third port, 3, 3 dash, and so on. This is N, N dash. So it is called N port network. Okay, so first port network, one port network, two port network, and N port network. Okay, so now the fundamental question is, how do you classify the networks? So far we have focused only on what? One port networks. But sometimes it is very important to analyze certain systems or certain networks using N-port network or two-port network. Anything more than one, you can call it N-port, and when N is equal to 2, then it is two-port network. So sometimes it is very important and interesting and useful also to analyze the given network using this n-port network approach. Okay, so the fundamental question comes now, how do you really understand the given network is a 1-port or 2-port or 3-port or n-port? How do you really understand it? How do you classify it? Do you classify the networks based upon the terminals available? That means the physical structure of the network. Or else you classify using the analysis. I would definitely say that based on the analysis, you divide the networks into categories. Are you applying 1-port network analysis? You apply. What is 1-port network analysis? Simply, we have applied already the node analysis, mesh analysis, and all those things. But what is the n-port network analysis? Any physical system that can be modeled, okay, as an n-port network or a 2-port network. I told you already n-port and 2-port I use here and there. Don't worry about that. If n is equal to 2, then it is a 2-port network. So any physical system or physical network can be modeled into an n-port network, provided if the physical constant of that particular network are invariant all the time. That means the physical constants like RLC values are not at all changing at all. They are not varying with respect to the variations happening in load or source. Source value changed, load value changed. Okay, then the physical constant won't change. Or else assume that the temperature is constant and some other variations are not happening at all. Okay, let us say then RLC values are constant. For example, transmission line. Ideally speaking, RLC values are always same for a transmission line. Of course, when the temperature changes, when the environment changes, then definitely that will have an impact on RLC values also. But in analysis point of view, we generally assume that there are no variations are happening. Particularly in the source and load, you can't stop it because load demand may change and the source definitely has to supply according to the demand. But irrespective of the variations that happen in the source and load, if all these physical constants are physical values or physical parameters are constants or invariant, let us say, then that particular network can be modeled into an n-port network or a 2-port network. You understand, all of you? Now, once the n-port network is modeled, then you have to analyze it. How do you analyze it? You have to replace that network by a black box, and the black box is described by certain parameters called Z parameters, Y parameters, ABCD parameters, inverse ABCD parameters, hybrid parameters, inverse hybrid parameters, like that we have. Understand? So simple it is. Now I have a facility now here and I am in need of converting the given physical system into an n-port network, because the analysis will become easy for me. I can easily analyze. For example, you take electric power system, you can treat it as an n-port network, and all the calculations can be happened very easily. You take a transmission line, it can be modeled or it can be represented by a 2-port network, and I can really do a lot of things and replace it by a 2-port network, and 2-port network is described by transmission parameters like ABCD. Then I can do a lot of analysis on that. So I don't bother about what is happening inside that box, but I bother about how the variables are changing. These V1, I1 and V2, I2 are called 2-port network variables. So I'm interested to find V1, I1, V2, I2, but I'm not interested in what is really happening, the voltage or current inside the box. Because inside the box is a black box now, because their physical parameters are invariant all the time. You understand, all of you? You take an example of even operational amplifier. Operational amplifier is also replaced by a hybrid parameter model. Yes or no? A transistor or an amplifier. You can replace it by a black box and described by a set of hybrid parameters, because their physical parameters are invariant with respect to the variations that happen in source and load. I hope you understand now what exactly the two-port network or n-port network. You can't identify this is a two-port network, that is a three-port network, that is an n-port network, that is a one-port network. You cannot identify like that. It depends on the given system and whether the system parameters are invariant all the time or not, that you have to check. If that is there, then you replace that entire system by a black box. That black box is described by a set of parameters called two-port network parameters or n-port network parameters. Then you can go further in the analysis. That analysis will become very, very easy. In such case, it is much superior. The analysis will become much superior and better than the one-port network analysis. In one-port network analysis, you have to obtain the equations using node mesh analysis, KCL, KVL. You have to obtain all the equations and you have to solve it. But when the system size is growing and bigger, okay, then definitely that will become very tedious in that aspect. Therefore, we classify the networks in the analysis point of view. Now onwards, we can understand just by looking at the network, can I really apply this two-port network analysis for the given system or n-port network analysis for the given system? You understand all of you, okay? So all electrical and electronic students, you study transmission lines. Electronic students are studying communication systems, okay? The physical transmission line which transfer the signal from one place to other place. And all electrical students are going to study the transmission lines, electric power system. There you are going to use this comfortably, this n-port network analysis or two-port network analysis. And electronic students are also using an operational amplifier and power amplifier, okay, and transistor modeling. You are using this two-port network analysis only based on the explanation that I have given here. Understand all of you, okay? Well, so now once the n-port network is modeled, you can see the variables. For a two-port network, you have two pairs of terminals, therefore you got four variables. Out of these four, two are independent. Okay, two are independent. So if two are specified, the other two can be calculated. So V1, I1, V2, I2, out of which two are independent. If those values are specified, the other dependent values can be calculated. If, for example, I know V1, I1, then I can find V2, I2. If I know I1, V2, then I can find the other two. So I hope you understand the point. Okay. So here, now what is the condition that you want to apply the two-port network analysis for a given system? Okay. This analysis will help you a lot in many cases like electric systems, electronic systems, control systems. Understand all of you, okay? But what is the condition? The physical parameter values like RLC, physical constants, are invariant all the time. What are the physical constants? Most of the times the RLC only, right? For a transistor and operational amplifier, the physical constants are something else. You may have gain and something like that. But most of the times you have RLC values. If RLC values are invariant all the time, you can model it as a two-port network or n-port network. And you can replace it by a black box, and the black box is described by a set of parameters called two-port network parameters or n-port network parameters. Understand all of you? Clear? Well, now let's come to the representation of lumped representation of two-port networks. I take an example of a transmission line. The transmission line can be represented by transmission line modeling. Lumped parameter representation. And distributed parameter representation. Representation. Okay, lumped parameter representation and distributed parameter representation. Any transmission line can be modeled. Okay, this is a transmission line. A single phase transmission line will be modeled, because if each and every small elemental section, if I divide this into n number of elements, Let us say this is of 1 kilometer. If I divide that 1 kilometer transmission line into each of, small elemental section with a 1 centimeter transmission line, let us say. Okay. So each and every piece, usually transmission line is modeled as what? Resistance, inductance, conductance, and capacitance. Series elements as well as what? Shunt elements. Yes or no? So these are called series elements, these are called shunt elements. Now, if I replace each transmission line by series elements R, L, and G, C, then when I divide the network into different sections, okay, then I can model each transmission line, because this is one small transmission line, this is another small transmission line. Like that, you have a big transmission line is divided into small pieces, and each small piece is considered to be regarded as a transmission line again. That can be modeled like this. So therefore, you will get what you can really represent it by like this. Now this is one small section, and this is another small section. Yes or no? And so on, and so on. I will have and so on like this. Okay. So this is what sending end, and this is what receiving end. So what happened here? All the parameters, this R, L, G, C, are distributed among the total length of the transmission line. This representation is called distributed parameter representation. What is this representation called? Distributed parameter representation. Now, lumped parameter representation is something different from this, because in the distributed parameter representation, the calculation will become very tough. Okay, you have so many number of loops and so many number of nodes, then obviously the analysis will become difficult. If you represent the transmission line using approximate models, that is lumped parameter representation, the total length of the transmission line, let us say the impedance offered by the transmission line is Z. Say the admittance offered by the shunt portion of the transmission line is Y. Now, if the total impedance is assumed to be divided into two parts, the first part is, say, Z by 2 is concentrated at the sending end of the transmission line, and the other half is concentrated at the receiving end of the transmission line, and the total admittance is assumed to be at middle of the transmission line, then this representation is called lumped parameter representation. Understand all of you? Okay. So this is called T model or T section, you call it. If you assume that the total impedance is assumed to be in the middle of the transmission line, and the total admittance, half of the admittance is at this sending end side, and half of the admittance is at the receiving end side. Okay, receiving end side, then this is also called lumped parameter representation. So this is T model, and this is pi model. You understand all of you? Okay. So transmission line can be represented in two different ways. One is a lumped parameter representation, the other is a distributed parameter representation. If all the parameters of the transmission line are distributed across the total length of the transmission line, that representation is called a distributed parameter representation. If the impedance and admittance are concentrating at one places, at the sending end or receiving end or in the middle of the transmission line, then that representation is called what? Lumped parameter representation. Understand all of you? Okay. Well, so the other types of sections, lumped sections, not only T, pi, okay, it's not related to the transmission line, but you can model different other systems into a bridge section, because this is the first one, let us say T section and pi section, and third one is bridge section. Mostly use these bridge sections or bridge model in filters, attenuators. Okay, filters and attenuators usually you apply. This is called bridge. You also use lattice section or lattice model. This is also lumped parameter representation. Lattice section. You generally use the communication systems or else filters, let us say, or attenuators in this model, bridge section as well as lattice section. Understand all of you, okay? So this is how you understand, I think, the two-port network or n-port network, how we really design or model a two-port network and how we go for two-port network analysis. The advantage with the two-port network or n-port network analysis is that the entire physical system is replaced by simply a black box that can be represented by a black box. The black box is characterized by certain parameters like Z parameters, Y parameters, ABCD and all. And once you model and replace it by a black box, you can embed this black box wherever you want. You understand? And you never worry what is happening in the black box. You worry about only the variables, V1, I1 and V2, I2 variables. That's it. Okay. So students, I think you understand, you got a pretty good idea on how the two-port networks are applied. The concept of two-port networks is applied for a given system. It's very, very important concept. The analysis will become easy, especially when the physical network parameters are not varying or invariant all the time with respect to the load and source variations. Okay. So that's really interesting part of the networks we can understand. Okay. Now I take the general representation of the two-port network. We already understood. Two dash, 1 dash. It's a two-port network. The voltage at this point is V1 and this is I1, current. The voltage here it is V2 and this is I2. V1, V2, I1 and I2. These are called two-port network variables. Understand all of you, okay? We call them as what? Two-port network variables. And the size of the two-port network parameters, because V1, I1, V2, I2, there are 4 variables. Yes or no, all of you, okay? There are 4 variables and 2 are independent. So you'll get 2 equations. 2 equations, but 4 parameters you will get. Understand all of you, okay? So now the relation between, based on the relation between the V1, I1, V2, I2, we define the set of parameters. So what are the set of parameters? Two-port network parameters, you call them. Two-port network parameters. Network parameters. Based on the relation, you can define, okay, Z parameters. Z parameters. In Z parameters, you will have V1, V2 is equal to the Z matrix in terms of I1, I2. Now these two are independent. If you can specify these values, the other two can be calculated, provided this particular matrix is known. But how many elements are in this matrix? Are there in this matrix? This is 2 by 1 matrix. This is 2 by 1 matrix. Then this should be what? 2 by 2 matrix. Yes or no? So therefore you have 4 parameters. So two-port network will have 4 parameters. Z parameters. There are 4 parameters. One Z11, Z12, Z21, Z22. That's it. Similarly, Y parameters. You will have I1, I2 is equal to Y, again V1, V2. This is also 2 by 1, 2 by 1, 2 by 2 matrix. Next, third one is transmission parameters or else ABCD parameters. V1, I1, ABCD, V2 minus I2. V2 minus I2. Again you have, look at this, 2 by 1 and this is also 2 by 1. Then this will be definitely 2 by 2 matrix. Fourth one. Inverse transmission parameters. V2, I2, A dash, B dash, C dash, D dash parameters. V1 minus I1. If this is a transmission matrix, then this is inverse transmission matrix, you call it. Okay. If this is Z matrix, inverse of Z will become Y matrix. Okay. And fifth one is hybrid parameters or H parameters. So what do you get here? V1, but I2. H matrix, but I1, V2. Sixth one is inverse H parameters, inverse hybrid parameters, or else G parameters, you call it. You have I1, V2, G matrix, and V1, I2. This is inverse of H matrix only. So totally we see 6 types of parameters. Okay, 6 types of parameters. Out of these 6, basically there are 3 types of parameters. Inverse of each will give you another parameter here. So finally you got 6 types of parameters. And the size of this Z matrix, Y matrix, transmission, inverse transmission, H and G depends on what type of two-port network, what type of network you're taking. Are taking 2-port or N-port or like that. If it is N-port network, you will get N by N. If it is 2-port network, you will get 2 by 2. 3-port network, 3 by 3. Like that you will be getting. Understand all of you, okay? So these variables will also change now. 3-port network means V1, V2, V3. N-port network means V1, V2, V3 and so on Vn. I1, I2 and so on In. And Z11, Z12 and so on Z1n. And so on Zn1, Zn2, Zn3 and so on Znn. So like that what is happening here, N by N matrix you are getting. Okay, so it's easy for us once you understand 2-port network analysis, the same thing you can apply for even N-port network also. 3-port, 4-port, N-port, anything it is possible. So the concept is same, only the size of the system will change. Understand all of you, okay? Well, so I think all of you can note down this. Please note down quickly. We can move on to the types of parameters, how we define and all, we can go. Okay, so please quickly complete that part. Now put the heading Z parameters. The first one is Z parameters or impedance parameters or open circuit parameters Okay, we call different names are there, open circuit parameters, impedance or Z parameters. So just now we have seen V1, V2 is equal to what? Z11, Z12, Z21, Z22 into I1, I2. So you will get now V1 is equal to Z11 I1 plus Z12 I2, equation 1. V2 is equal to Z21 I1 plus Z22 I2, equation 2. Or equation A, let us call it AB. I generally call this is A, this is B. Equation A, equation B. Now let us define these parameters. How we define the parameters? We need to define Z11, Z12 now. How you define? Z11 is defined V1 by I1 when I2 is 0. Suppose if I2 is made 0, because these two are independent, right? So two variables are independent. If I make I2 0 first, then I1 0 first, then I get V1 by some other variable I'll get, right? So V1 by I1 when I2 is 0, you define Z11. So Z11 is an input impedance because input voltage by input current will give input impedance. But under what condition? When I2 is 0, this is called condition. This is called condition. Under this condition only you define what is Z11. Okay, it's not simply V1 by I1. It is V1 by I1 when I2 is 0. So I2 0 refers to what? I2 0. Current 0 refers to what? Open circuit. So open circuit is already input impedance. So input impedance. Input impedance. Similarly, when you make I2 0, you can define another parameter. So what is that? Z21. What is that? V2 by I1 when I2 is 0. So what do you get here? V2 by I1. Output voltage by input current. If output voltage by output current, then I can call it output impedance. Input voltage by input current, it will be input impedance. But output voltage by input current, I can use transfer impedance. But this is under open circuit condition. Therefore, open circuit transfer impedance. I use forward transfer impedance because I get two transfer impedances. So forward transfer impedance. Okay. So to get this Z11, Z21, I should make I2 0. That means the circuit will be something like this. The network will be something like this. This is a two-port network. Okay. Now I can open these two terminals because 2 must be open because I2 is 0. So I2 is made 0. To make I2 0, I must open it. But I will measure open circuit voltage. Yes or no? So what is the open circuit voltage here? V2. Understand? Whatever the voltage I measure across 2 and 2 dash, that is nothing but V2. Okay. Similarly, this is 1 1 dash. Say this, I excited 1 1 dash with V1 and I injected some current I1. So this is how I can make the circuit, or I must apply the conditions like this, and I must apply that condition I2 0 and measure with the help of voltmeter V2 here and connect the source V1 and determine what is V1 and measure what is I1 and find the ratio of V1 to I1. You will get Z11. Find the ratio of voltmeter reading V2 by ammeter reading I1 here, then you will get Z21. This is how you determine the parameters of any given two-port network. Understand? Okay. Well, now this is what when I2 is 0. When I1 is 0, you will get Z12 is equal to V1 by I2 when I1 is 0. Again, this is input voltage by output current. That means transfer. This is also transfer. This is, if I call this is a forward transfer, then this is going to be reverse transfer, but under open circuit conditions. So open circuit reverse transfer impedance. Okay. Z22 V2 by I2 when I1 is 0. Open circuit output impedance. Okay, this is when I1 is 0, right? So when one variable is 0, then you will get two parameters. When other variable is 0, you'll get another two parameters. Finally, you need four parameters here. So I just understand here to get these parameters, I must make the arrangement something like this in the given physical system or physical network. 2, 2 dash, this must be V2 and this must be I2. I'm injecting. I can measure this using an ammeter. I know how much voltage I'm giving, but still I can measure by connecting voltmeter across it. But I1 must be made 0, right? And if I connect a voltmeter here, I'll get V1. Understand? Okay. So this is how you can measure Z1 to Z2. Now, I can draw an equivalent of a two-port network using these two equations. Okay. I understand that V1 is equal to Z11 I1 plus Z12 I2. This is one voltage. This is another voltage. If I add these two voltages, I'll get another voltage. So voltage is getting divided. Understand? Voltage gets divided when you have series combination, let us say, when current is same otherwise. So current is same if I maintain and voltage gets divided, I can go for series combination. So input port side, if I take series combination of two elements, one element is having Z11 I1 product, the other element is having Z12 I2 product. If I arrange these two in series and give some V1, the voltage will be divided. That two voltage will be giving total voltage. So therefore, I will arrange. This is called equivalent of any two-port network in terms of Z parameters. In terms of Z parameters. So tell me now, what is that? Equivalent. This is Z11, 1 and 1 dash. Obviously this is V1. Obviously this is I1. So Z11 into I1 will give what? What is the voltage? Z11 into I1 plus minus polarities. And now if I take the help of dependent source, because this is I2 which is not related to first port but it is related to second port, therefore let me take the help of a dependent source. I have no other option. I'll take the help of dependent source. So what is happening here now? This is plus minus polarities with a current direction. Z11 into I1, you get Z11 into I1 plus Z12 I2 will be giving you what? V1. So first equation got satisfied. Second equation, in the similar way, if I connect again the same way series combination on the second port side, 2 and 2 dash, Z22, this is I2 plus minus V2, Z21 I1. So I hope you understand now. So same way, like you have plus minus Z22 I2. So you see now V2 is equal to what? Z22 I2, Z21 I1. Addition of these two. So second equation is also satisfied. That means I'm able to construct a two-port network, okay, equivalent of any two-port network in terms of Z parameters. If I know a two-port network and its parameters, I can construct again equivalent of that two-port network. Okay, so this is now represented by a black box. Understand all of you? Okay, so V1 I1 and V2 I2. Another important concept, that condition for symmetry and condition for reciprocity. Condition for symmetry. Condition for symmetry and condition for reciprocity. Reciprocity. Condition for symmetry and condition for reciprocity. What is the condition for symmetry? If Z11 is equal to Z22, then the given two-port network is symmetric two-port network. Symmetric two-port network. Otherwise, a non-symmetric two-port network. If Z12 is equal to Z21, then it is called reciprocal two-port network. Otherwise, it is non-reciprocal two-port network. So, condition for reciprocity and condition for symmetry. if Z11 is equal to Z22, condition for symmetry, thus that given two-port network is said to be symmetric, or else it is non-symmetric or unsymmetric. Similarly, Z12 is equal to Z21, it is called reciprocal. We studied reciprocity theorem. In that, the ratio of output, okay, the output response by input source value does not change, even if the source and response are interchanged. Look at this here. First, you have taken V2 by I1, then you have taken V1 by I2. Understand all of you, okay? First, you have given I1 source at the input port side and you measured voltage output port. Now the same source, you have connected the second port terminals I2 and you measured the voltage at the first port terminals where the source was connected earlier. So you measured it. Now the response to source value must not change. Okay, if they don't change, that means Z12 is equal to Z21, then that is called reciprocity, condition for reciprocity. Reciprocity theorem is satisfying. Therefore, you will get reciprocal network. The network which satisfies the reciprocity theorem is called reciprocal two-port network. Understand all of you, okay? Well, now I think you understand. Suppose if I give a network and ask you to find whether it is symmetric or non-symmetric, what will you do? You find Z11 and Z22, then see whether they are same or not. Based on that, you will decide. Yes or no, all of you, okay? And I will also ask you whether the given two-port network is reciprocal or non-reciprocal. Then what will you do? You may find Z12, then Z21. Yes or no, all of you? Based on that, you will confirm. But it is unnecessarily the time-waste process. Okay? Don't waste your time by finding Z1 to Z21. Simply you see the given two-port network. Okay? Whether the given two-port network is having any dependent sources or not. If any two-port network contains dependent sources or dependent source, let us say, then definitely the condition for reciprocity will violate. It will not satisfy the condition for reciprocity. Hope you remember in the reciprocity theorem we discussed in the first chapter, any circuit, if it contains a dependent source, the reciprocity fails. Any circuit, if it contains dependent source, the reciprocity fails. So therefore, let us apply the same concept here. If the given two-port network consists of any dependent source, the reciprocity fails. If the two-port network does not contain any dependent source, then reciprocity will be satisfied. So there is no need to find Z12, Z21 and waste our valuable time. Just by looking at the network, two-port network, and identifying whether there is a dependent source or not, you can easily confirm it. I hope you understand the point. Okay. So please note it down and also write down that important point. If two-port network contains any dependent source, the condition for reciprocity fails. That means Z12 is not equal to Z2. Please note on this, all of you, quickly. So the second one is Y parameters. Admittance parameters. Short circuit parameters. Okay. V is equal to Z into I. This we have seen already in the case of impedance parameters. Then I will become what? Z inverse. Inverse of Z matrix. Which is nothing but Y of V. Therefore, Y is equal to inverse of Z. Total Z matrix inverse, not individual parameters. Okay, you can't say Y11 is equal to 1 by Z11. No, not like that. The matrix inverse you are supposed to consider. Okay. Now, I will go with I1, I2 is equal to Y11, Y12, Y21, Y22 into V1, V2. Okay. I1 is equal to Y11 V1 plus Y12 V2. Equation 1. I2 is equal to Y21 V1 plus Y22 V2. You call it equation A and you call it equation B. Okay. Now let us define. What is Y11? When V2 is 0, you will get two parameters. When V1 is 0, another two parameters. So therefore, let me put now V2 0 first. So what do you get here? Actually here, Y11 is equal to I1 by V1 when V2 is 0. You call it short circuit input admittance. Y21, I2 by V1 when V2 is 0. Short circuit, let us say forward transfer admittance. For this, you require the network to be connected like this, 2, 2 dash. V2 must be made 0. So let me make this V2 0. But if I connect an ammeter here, because it is a closed path, definitely it reads some value. Say that ammeter value, which it reads I2. Some I1 is injected, 1, 1 dash. Say this is V1 because the voltage across 1, 1 dash terminals is V1. I can also connect a current source. That's not a problem. Okay. You can connect a voltage source, a current source doesn't make any difference. But I'm connecting current source in this context just for difference because I've already connected voltage source. Okay. So if I connect current source I1 and the voltage V1 across 1, 1 dash, across 2, 2 dash, V2 0, but I2 is there. Then I can measure because ammeter value here, current source value I know. I connect one voltmeter to understand what is V1. I know V2 0. I connect an ammeter here to understand or to know I2 value. Once these values are there, if I substitute here, I'll get Y11 and Y21. Understand all of you? Okay. Well, similarly, I go with other conditionals. Please note down that. Now I think you understand. You can note down along with me. Now V1 0. Y12 is equal to I1 by V2 when V1 is 0. Yes or no? Okay, Y12 is equal to I1 by V2 when V1 0. So short circuit, reverse transfer admittance. Y22, I2 by V2 when V1 is 0. Short circuit, output admittance. Short circuit, output admittance. So how do you get now the network? 1, 1 dash, it is 0, V1 is equal to, but you measure some current I1. Yes or no? 2, 2 dash, you connect one current source here. Say this is I2, whatever the current is available at 2, 2 dash, 2, 2 dash, that is called I2. Whatever the voltage available across 2 dash is called V2. So this is a two-port network. Now all the values are available here. You measure current using ammeter, connect voltmeter here V2, connect an ammeter to understand how much current is flowing here. You will come to know I2. Then substitute here and get the values. Okay. Now I would like to construct equivalent of any two-port network in terms of Y parameters. In terms of Y parameters. Okay. So according to the first equation A, I1 is equal to I11 V1, Y12 V2. This is current should divide. This is one parallel branch, this is another parallel branch. If I connect these two parallel branches, the current flowing through this will give you total current. So I go for parallel combination on the input port side. 1 dash. I have, this is V1, this is I1, yes or no? This is I1, Y11 into V1. What is the current flowing here? Y1 to V2. I am taking the help of dependent source because V2 is the one term which is related to the output port. Okay. Similarly, if I do the same parallel combination on the output port side, because now this is satisfied, look at this. What is the current flowing here? This current is Y11 V1. And this current plus this current will give you what? I1. Now, Y21 V2. Y22. 2 dash. V2 and this is I2. Look at this now. So what is the current flowing here? Y2 to V2. So this current plus this current will give you the total current. Now this is what actually here. Two-port network. Any given two-port network can be replaced by this equivalent in terms of what? Y parameters. Okay. Now, condition for symmetry and condition for reciprocity. Symmetry and reciprocity. Conditions. You know that in Z parameters, you know what is the condition for symmetry and condition for reciprocity. But you also know how to express Y in terms of Z. Okay, because you know the condition for symmetry and reciprocity in terms of Z. If you want to know the condition for symmetry and reciprocity in terms of Y, express Y in terms of Z. So what is Y? Y is nothing but Z inverse. So what do you get here? Z2 2 by. This is nothing but what? Z11, Z12, Z21, Z22 inverse. So you have determinant 1 by del Z. This is Z11. This is minus Z12. This is minus Z21. So I think you understand now why Y11 is nothing but Z22 by del Z. Y12 is minus Z12 by del Z. So therefore, it's very important. Y21 is equal to minus Z21 by del Z. Y22 is equal to Z11 by del Z. Okay. So this is how you express Y parameters in terms of Z parameters. Now if you apply the conditions, okay, if you apply the conditions from this, if Z11 is equal to Z22, it implies Y11 is equal to what? Y22. Just see here. If Z11 is equal to Z22, then it becomes Y11 is equal to Y22. Therefore, this is nothing but condition for symmetry. If Z12 is equal to Z21, it becomes y12 is equal to y21. Check here. y12 is equal to y21. Then it's nothing but condition for reciprocity. Understand all of you? Okay. So this is how we can define y parameters and condition for symmetry and reciprocity. Please quickly note down. Okay. So we stop the session here, and the next session we will